Today we're going to look at one of the most important experiments that prepares our year 13s for paper 3. It's about designing an investigation using what we call whirling the bung experiment. So using all the equipment that we've got on the board here, could you design an investigation to work out the unknown mass of this rubber bung? So you've got your timer, you've got your rubber bung, you've got a weighing scale, and you've got this plastic tube that you hold the string, weights, crocodile clips, and ruler. So take a moment and try and think about how you're going to do this, okay? So basically this experiment goes like this. It's circular motion, right? So we call that whirling the bung because that's effectively what you're doing. You're whirling a bung like that. So it's doing circular motion, right? And the first thing when I asked the boys to do that, they thought that they were going on a vertical plane. So that's a vertical plane. And obviously this one is on a horizontal plane. So let's break it down and have a look at what's happening. So the key thing to identify here are that there are two masses. A small mass A here of the rubber bung is what we want to find. And capital M here is the mass of the weights that we add. So this, the small weights that we're adding to the end. So what's the effect of that? Why are we changing that? Why are we adding masses? Well, the masses here, they will give you that tension in that string. What's causing centripetal force here? So if we look at centripetal force is equal to mv squared over r. That centripetal force is provided by that tension. And what's causing that tension is this. So if we rewrite this now as tension, which is equal to the masses attached to the end of the string is equal to mv squared over r. Now we've got an expression. Linearizing this is a key skill. So let's try and linearize it, see what we can change, what we're going to measure, what we're going to keep the same, and how to find the unknown. So if I rewrite this as capital Mg over mv squared over r, and I keep v squared on this side, and I send the r to the other side, divided by the m. I have now effectively linearized this equation. So if I have this on the y-axis, this on the x-axis, this will effectively be my gradient. So this will be my gradient. Now, so if I'm changing mass and I'm measuring the velocity, I'm actually measuring the velocity, but I'm not plotting velocity. I'm plotting velocity squared. That should be a straight line that goes for the origin. It's a direct proportion. And the gradient here should be equivalent to this. So what I'm going to keep the same, I'm going to keep r constant. How am I going to do that for you to figure out? G is constant and mass is the unknown. So as you change m, as you change in m and you whirl in the bung, your change in m, velocity will change. So the big question now is for you to think, how do I do v? It's circular motion, isn't it? So v is 2 pi r over t, time period radius. Some of you may say, sir, where does this come from? Well, this is r is equal to r omega. R omega. Omega is 2 pi by t or 2 pi f. In this case, 2 pi by t, and it gives you the same thing. All right, next part. What should your table of results look like? Try and think about what the table of results should look like. This is another skill that you'll need for your paper 3. And why am I talking about this? There you go. AQA could ask you like a random equation that you've never come across in your life. And they'll ask you to design an experiment. So this experiment here, this designing of this experiment, doing this experiment, finding the unknown, linearizing, helps you in questions like this in paper 3 for 5 marks. A horrible equation, but look what I did. I isolated my independent variable, my dependent variable, and my control. And then I decide what graph I'm going to plot. You've done that again previously in every single required practical. Here's an example for terminal PD. So this is how the student will do this in the actual classroom. But there's so many issues with this practical. Think about it. Is that bung whirled in the right plane? Is it perfectly horizontal? What about that crocodile clip? If you're whirling it too fast and the crocodile clip is preventing that string to move up, it's generating another force which could affect your experiment. So students should be able to think about how do we minimize those. And finally, right, we get our boys to then go on and do this experiment, but the table of result should look like this. Your independent variable in kilograms. This is there's 2 times, by the way. This time is the time taken for 10 oscillations. So you repeat it, you do an average. Effectively, you don't want that. You actually want the time period. Okay? And after the time period, you can then work out your V. But again, V is okay, but you can't plot V. You got to plot V squared against M. How do we get V squared? 2 pi r over t squared, that whole expression. And this is another mistake that people do. In the table of result is V squared. So you've got to write meters squared per second squared, because this quantity has been squared, so the unit gets squared as well. And eventually, then the students can find the gradient, and this is our results, and they can work out the unknown. Thank you.